welcome to the course on FPGA based signal processing systems, in which that we had looking at the arithmetic basics. So the adders, how the adders can be used in this parallel prefix circuit, or the adder the speed can be faster by using these techniques. So the adders and subtractors, if you see the 4-bit carry ripple carry adder or the n-bit ripple carry adder, if you recall the Verilog code which we had done for 4-bit ripple carry adder, in which the carry ripples through the previous stages. So the first stage may be a half adder if you don't use it as a subtractor, otherwise it needs to be a full adder. So the carry in will be, that is 1 or 1 in the case of the subtractor, or otherwise it is going to be 0. So accordingly the number we are going to, the 4-bit the ripple carry adder can be modified according whether it can be used as an adder or a subtractor. So the most arithmetic basic ones use this digital computer for the addition. So the half adder we had learned that is it performs A and B, that is two input bits, okay, so which is added in the half adder. It cannot take carry in it. So we know the inputs and the sum and carry for the half adder circuit, which sum is 0 and in this case also 0, where carry is generated, whereas in the other two conditions, this is the input conditions, the sum is 1 and carry is 0. So this half adder operation, this mimics the XOR logic, and this is the AND logic. So we use one XOR gate and a logic gate and instantiate them and made a half adder, and then using two half adders we can also have the full adder or 1-bit adder. So in this case the XOR gate function and the carry is given over here, whereas in the if we have this, it cannot accept the carry, as I said. So it's not possible to cascade the half adder to contact in order to make the n-bit binary adders. So half adders cannot be used for making the cascaded structure, whereas it can be a first step of the addition in n-bit adder. So this is the structure of the of adder, where we had Verilog we have developed the Verilog module and simulated this as well. So the simulation, the functionality is simulated, and then using this half adders can we make this full adder? Yes, this full adder function can be made, and it is, you know, that it is a combination of this ABC addition of one bit adder which has 3 inputs. C is the C in which we take. So C out and sum also can be obtained through this. So the expressions we know very well, that A XOR B XOR C. So in the A XOR B, B XOR C, sorry, and then carry is generated by and logic through and OR logic, where AB, AC and BC are doing the AND function and this ORing them get. So this can be minimized also with as AB, this function, and the common one C can be taken out and to have A plus B. So the reduced function, which can be written if it is a full adder, AI and BI, CI is the input and SI and SCI plus 1. So this full adder operation, which now done with the two half adders, which is AI and BI, this two I can be of any stage. Ith stage is shown. In an n-bit adder you can have this multiple such units. So this is one full adder structure in which you have this XOR operation of A and B, and that is XOR with C. So this is this carry in which is coming into this C, and you get the sum. So the carry which is generated here, AB, and or you can use 3 AND gates and then 1 OR gate as well. So that means AB, AC and BC. That's what the configuration we had done in the Verilog module. So in order to minimize the number of gates, here we have used AB, this one AB, and then the output is ORed with the here again the cases which can be simplified to A and B. This is C, and the another AB which is equivalent to the XOR operation, and then the C. Okay, so this would also mimic the same behavior. I mean, the logic would be similar. So this is nothing but this is one half adder and this is another half adder, and adding the two carries would give this full adder carry. So the I plus 1 carry is using this ABC. We have this two half adder function. So the full adder can be realized using this two half adder also. If you write a Verilog module for one half adder, and then you can instantiate it by two half adders with one more OR gate can mimic the behavior of the full adder. So this full adder, if you want for the n bit carry, n bit ripple carry adder, so you need to have this same module can be instantiated again once again. So the smallest half adder module can be used as a full adder module, and then full adder module is again used for the n bit addition. So in this case, now what we are going to see that a full adder can be implemented with two half adders and an OR gate. So this is what we had done already. So here A, this is half adder, and I showed you the C is taken with the XOR operation here to have the sum, and these two are, so two half adders have shown over in the previous circuit. So now we will going to analyze this, how many we just change this circuit with the NAND gate inputs, and then see them how the NAND gate operation, NAND gate input can be to make it uniform and find the gate delays of this. Okay, so now if you just replace this, it can be this way around. So A and B are the inputs and the C also the carry in. So the one XOR gate which is changed over here, this XOR operation, and this is another XOR operation. Okay, so so the output of this given, and given the first XOR gate is given to the second one, and similarly C is taken here. So these are all made two input NAND gates, and the OR function, and there are one AND function over there. So those things AB AND, which is coming over here, and the XOR and this mid AND, and this is AND, so get the C out. So you have this for three more AND gates, and here 1 2 3, this is four NAND gates for is 4 NAND gates, again 3 NAND gates. So totally 4 plus 4 here 8 plus 3 here 11 NAND gates used for this function. So if you have one NAND gate and module, which can also be you made a ladder. So the idea here is that to reduce the time for the ripple carry, how much time it takes in the, or you compute this, how much time it takes for the carry to ripple through. So for calculating the sum and the carry. So here we can see from AB to sum, this input to sum and carry to sum. Okay, so the carry to sum, if we take this here, it has 1 2 3, so 3 levels of 3 gate delays it is taking. Okay, so if we take, this is one gate delay, 2 input gate, NAND gate, so inside is considered to be 1 gate delay. Then the gate delay model, we are coming to the timing analysis part. So this has 3 gate delays, and here there is 3 gate delays. If you go from here to here, 3 gate delays, okay, and 3 gate delays. So this 3 gate delays cannot be obtained without the C. Okay, so C needs to be obtained after this 3, and C should be given, and then sum should be calculated. So if you directly see from here to here, it is 6 gate delays. From C to sum, it is 3 gate delays. And then from AB to the C out, you have this 1 and this is 2, and parallelly there is 1 more gate delays. So C to C out, this C and C out, this is 2 gate delays if this is available, because this will be calculated, this is having 3 gate delays, so this must have been calculated early. So you have C is available, and then it takes another 2 gate delays to compute C out. Okay, so with this gate delay operation, let us see that this is C. To sum, you have this 3 gate delays, and then here to here is only 2 gate delays. So if we consider this the whole thing in the case of 2 input, that is an AND gate implementation, so we can make this diagram just taking this A and B are input, C is the C in of any stage, this is C out. So this can be multiple for the ripple carry adder. So you have this 3 gate delays for intermediate sum, that is XOR output, and another 3 for, this is for another XOR gate operation. So 3 gate delays and 3 gate delays. So once you have this 3, to obtain the C out, this is only 2 gate delays. Okay, so you can see here, this is obtained, you have 2 gate delays to obtain 2 C out, or C to this C out. Okay, so again this is 2, we said C to C out. If we go for like this, this is 2 again. So 3, 3, and then C to sum, this is 3 gate delays. This is if we have suppose C in, and this is regarding this, which takes only 3 gate delays. So 3 and 3, these are justified, and the intermediate sum you can go. If you have this intermediate sum, the C out can be calculated with 3. So if we have all of them A, B, and then so this is the intermediate sum can be generated with 3, and to get the carry it is only 5. 5. So 5 gate delays. Okay, so if you want to directly compute this with the C, so here this is sum. Okay, so with this gate delay operations, what we have, so can we have the full timing structure? So one gate delay is actually the propagation delay through 2 input NAND gate, what we assume, as I told in the previous slide. So the ripple carry adder, which is summing up the A and B of suppose 4 bits, A0, A1, A2, A3, in which this is sum will be S0, S1, S2, S3, and the C out will be C4, whereas the input C in is C0. So with this inputs, the adder looks like that, C0 for 4 bit. So adder looks like C0. So from this bits you can calculate C0 to C1, C1 to C2, C2, C3, and C4. This is C out. S0, S1, S2, and S3 are the sum. From this bits, now if it is going to generalize the timing involved in this. So each one A0, A0, A1, A2, and this is n minus 1. If it is going to be 4 bit, this is 3, A3, and B3. So here is we have the C0 input. As we have seen 3 and 3, we take the sum 6 gate delays. Okay, and if you have C, and to get the sum only it is 3 gate delays. Okay, so in this stage, if you have C, it's taking only 3 gate delays at the last stage to get the sum. So whereas here first stage would 3, and then here we have seen, and to calculate the carry it is C1. So 5 gate delays. Okay, so 3 plus 2, this gate takes 5 gate delays. If you look at the carry alone, so 5, and once you have the 5 and another 3 to here to get the sum. Okay, here, and 7. So each stage would, from this carry to this carry, if you look at, if you just recall this, here C2, this is only 2. Okay, so if you have the intermediate sum, it is taking only 2 gate delays. Have this intermediate sum, it is only 2. So 5, and then this will be 7 gate delays and 9 gate delays, and so on. So each stage would be taking 2 gate delays to generate the carry. So the sum is of course having the 6, and then plus this is having the 8, and you have another 2 for this, the 10, so, and so on. So we get this gate delays 6, 8, and 10. But what is the actual sum and the carry time which takes? So it has to ripple. So this carry, this second stage should wait for this carry to arrive. Okay, otherwise this cannot compute the sum here. Okay, so because it needs to, this gate delay depends on this this carry available here. So we need to have AB, the intermediate sum can be calculated. With this C needs to be XORed so that this 3 gate delays are fulfilled. So otherwise this cannot be independently done with the 3 plus 3 6 gate delays. Okay, so it looks this path, it is 6 gate delays. If we don't have this is going to be 0. Okay, so this is 0, and whereas in each stage C1 and then C2 it need to arrive, it has to wait for another 2 gate delays. So similarly the carries are getting rippled through, and once this carry is available and the intermediate sum is available, yes, it is easy to compute the sum within the 3 gate delays. Okay, so this needs to be added in the timing. So it has to ripple through to C0 to Cn. So the worst case delay, propagation delay, if we compute that T sum, it is the intermediate one, the first 5 gate delay, and last one takes the 3, because if once the carry is available and then the sum needs to be calculated at the last stage, and this is for the first stage sum. So the first stage sum it can taking instead of 6, if we have 3 plus 3, and then so the carry is involved. So if that is going to be 0, so 5 gate delays, and the I is I1 to n minus 2, the intermediate steps, intermediate full adders up to n minus 2, excluding the last one and the excluding the first one also. So n1 to n minus 2 takes this 2 into n minus 2 here, that is 2 times the n minus 2. Each one takes 2 gate delays in terms of 2 input NAND gate. So if we add them, this is 2n minus 4, this is going to be 2n minus 4 plus 3, and here it is 5. So you get 2n 8 minus 2n plus 4 here. So this is in the order of n. That's what I would like to say, that if to compute the sum, it depends on the gate delays, or depends on the n number of bits the addition needs to be done. So similarly, worst case propagation delay for the carry operation. So the carry also the delay for Cn minus 1. So up to the first stage, how much time it takes to get into the stage Cn minus 1, and then the last stage of 2. So this is going to be again the first 5, and then the n I to 2, and only the last stage which has 2. So this is 1 less here. So if we compute this here, 2n plus 3. So the carry also equally having the, for generating the carry we need this time. So the order, the propagation delays involved in the gates. So if we have one 2 input NAND gate has suppose a 10 nanoseconds delay, so then it depends on this. So we have at least on that 11 gate delays, and the number of bits, it is n. Okay, so the propagation delay is in the order of n. So order of n is the 2n plus 3 or 2n plus 4. So to calculate sum and carry. So this is because it has to wait for the carry to be generated in each stage and ripple through to compute the sum as well. So this is the performance of this n bit carry adder. So if we use this n bit carry adder, yes, definitely there will be propagation delay in the computation. So if we have this adders, and the subtractor can also be visualized in that way. For each adding operation, how we use this, how do we find the maximum here? In this case, it is going to be the worst case delay, which is 2n plus 3. And so we'll compute the critical paths using the timing analysis of for the design. So this worst case delays actually involves in the critical path computation. If we coming to the multipliers, the adders and the subtractors, instead of that, we look at the multipliers. If you want to multiply the two numbers, here we have this, suppose take the binary numbers. In the binary numbers we have the signed and unsigned multiplication as well. So considering the two numbers, suppose x and y, there are two numbers which needs to be multiplied. So unsigned number, or we'll have the signed multiplication as well. So x is a number, and x suffix I 2 power I is the representation of x can be represented. So I is varying from 0 to m minus 1, the number of bits here. So similarly y can be from 0 to n minus 1, this is m bit and n bit numbers of yj and 2j. So if you multiply the two x and y, so 2 is it's 4 bit, again this is 4 bit equal bit, so m plus n minus 1 would be the total summation. Okay, so here we can have the addition of the two things here, which is see that x cross x y 0 to m minus 1 xi 2 power I, and j is n minus 1 yj 2 power j. So adding this to summation xi, and this is also the x and y, and vary them, this is x 2 power I plus j. So which is also can be replaced with a, so this is how in the summation needs to be varied for I and j, and then getting 2 power I plus j. So it would in each stage, if we in this way we would multiply the two of them, that is m bit and n bit numbers. So if we take the binary multiplication which is unsigned, okay, so it can be done in two ways. One is the conventional way, what we do in the multiplicand and the multiplier. Suppose taking this as 5 bits of bit, that is number 5, this is unsigned, and there is a 11 value 11 which is also 5 bits. So to represent signed, we take this last bit, because this is 11, we made it 4 bit is required, and 5th bit is 0, and for representing 5 it is 3 bits 101. So we have to equalize this 0 has been shown here. So the 5 and 11 are multiplied, you will be getting 55 anyway. So what we do is this multiplicand, first we multiply with the multiplier 1, so you get this 10100, and then next bit of the multiplier is also 1, so repeat the same multiplicand here with 1 shift, and the next one is 0, so there is the multiplicand will result in multiplication result in 000, and the next case it is this is 1, so the multiplicand is repeated here with 1 shift left, and next is 0 here. So make this multiplication, that is AND operation, and then add. So and this is zeros and 1, so it's simply the AND operation, and gates and the adder circuit can be used for this multiplication. So 1 and this, adding this 1 and 1 will get 0, 1 carry, and 1 0 0. So this is 55. So this is a conventional multiplier. So there is no problem. It can, instead of having, these are called the partial products. So these partial products, generating all the partial products and adding all the partial products one time. So instead of doing this, means either we have to reduce this addition or the multiplication, the process in the to speed up this process, the multiplication process. So in this case, we have the single addition at the end of add up all the to add all the partial products is computed with AND gate and adder. So this partial product is with AND gate, and then this product is computed with addition. So now this is conventional. So if instead of having this, we have this unsigned binary multiplication. So these are the two numbers we had taken. So instead of it, first to take this initial partial product and take the first partial product, that is, this is the first partial product of multiplicand is multiplied with 1. So you get the first partial product and then add this two. So as and when the partial products are generated, add them. So here add it, here this is addition, and then shift to right, because this is shift right is a register which we can use a register for shift right operation. So shift right 1 bit and then again get the second partial product for this. So this multiplicand into 1, that is the second partial product, the addition and the second partial product, now add it here. So initial partial product is assumed to be 0, the first partial product added and then shifted, now this second partial product it added with this. So what we get is this number, and then shift once the addition, shift it right okay, and third partial product is 0. So partial products as and when generated, it is added and shifted. So the next one is the summation is here, and then shift right fourth partial product and then add this to here and shift right and fifth partial product. So we will get add this to the final partial product is this, and the product we get it by adding it. So this is not the conventional addition, but using the register, shift register, and the addition adder, we can perform this multiplication process using the adders also. So in this case, parallel addition on each stage. So you have to the computed one needs to be shifted and added here. Okay, speed of operation, which is depends on the time required to compute, number of additions required, that is depending on the number of bits we want to multiply. Okay, so this multiplicand has how many bits. So the width decides the addition time. Okay. So this is more faster compared to the conventional one. So this is within this one having the shift and add operation. So the unsigned binary multiplication, we had seen that the signed binary multiplication can be obtained with multiplicand, and this is actually the positive one. So we have plus 5 and plus 11 positive multiplicand. So the partial products can be generated when you deal with signed binary signed numbers. Then need to be the extension, sign extension needs to be taken care, because if the sign magnitude, if you remember that 0, the last bit represents the sign. If it is 0, then the number is positive, otherwise if it is 1, the number is negative. So here 0, first take this multiplicand and multiply, this is 1 partial product, and extend the sign at least up to 2n bits. So this is sufficient here to represent this 55, so it is extended up to 4. So similarly here next partial product is obtained from this, and shift 1, the sign extension needs to be done. So this is next partial product for the sign with the sign extension, and here the next partial product with sign extension, and this last one. So, and add them, so you get the 55, that is the product. So in the signed binary multiplication, this needs to be taken care, the sign extension needs to be taken care. Similarly, if we use the signed multiplication for negative multiplicand, so the multiplicand is negative, suppose this is taken as minus 14. For minus 14, the representation is actually the 2's complement. Okay, so the representation is 2's complement. Take the 14 number 1110, and then take the 2's complement of it, so we get the negative number 1000, which is represented in 5 bits. You can see the last bit which is giving the negatives. So the other multiplier is positive 11011011. With this we can first thing is this multiplicand, because the first multiply 1, so it is copied 10010, and extend the sign 11. So this is a negative number now multiplied, so needs to be extended 111. Similarly, the next multiplicand and extend sign extension 0, and the last one which is having 01001. Okay, so with this we can stop. We can have this also 111 and then add them to get the minus 154. Okay, so it is having 5 bits. Up to this, it is sufficient to have the number. So even if we have 111, that is not going to make any sense in the product. So this would be minus 154 with the signed binary multiplication. Apart from this signed one, we have this modular multiplication also, in the sense the multiplication doing it in unconventional ways, shift and add whenever the partial product is generated. Instead of generating all the partial product and then adding it, you can have this addition, either reduce the addition operation or this needs to be done. So for modular multiplication, suppose we have the number A which has 8 bits and the second number having 8 bits. So we can have them equally separated, like bifurcated, 0 to 3 and then 4 to 7. Here similarly 0 to 3 and then 4 to 7. Two sets of numbers can be taken and represent them as like this, A3074 is 30 and 74. So multiply them with them. Now the multiplication can be done with this first A30 and B30 and get this. And then we have this B30 multiplied with 74, so it's shifted, and the next one is this A30 multiplying to B. This is the third one, A30 multiplied with B 7 to 4, and then A74 multiplied with this. So you have the here you won't be having the one shift only, is A30 and this, and the next one is B30 to the A74, and similarly this one to this. So if we add all of them, you get the partial products for 0 to 3 over here. If you add all of them, get the partial product for 4 to 7, and then 8 to 12, and then 12 to 15, 13, 14, 15. So 4 bits partial products can be obtained together. So instead of having this 8 bits, so have this number multiplicand and then multiplier, and repeating the multiplicand depends on the ones, and then shifting and adding. So this would be giving the modular multiplication would result in the faster operation. So with this we had seen how the addition of the ripple carry adder, what is the time involved in this sum and carry generation if you have n bits, okay, how worst case delay can how it is getting affected due to the ripple through addition, and the multipliers, or what is the conventional and unconventional way. If you have this multiplicand and multiplier, both of them also negative, in that multiplication also be done, that is negative multiplication. So negate the numbers and then multiply them as such in that case. So the third category is that modular multiplication. If you have the numbers 8 bits and get them separated into 2 and get the partial products in this way, so which is having the larger number separating them into smaller ones, and multiply and shift, multiply this and shift, arrange it in this fashion, this is important, and then getting the partial product in that case. With this we have done the addition, very basic ones are addition and the multiplication. We will see the critical paths and then the Codic algorithm, also the few more number representations in the next lecture. Thank you.